now that we've introduced sinusoids and phasors, let's look at the phasor relationship for circuit elements, and specifically resistors, inductors, and capacitors. Okay, and so how can we use these relationships to go from time domain to frequency domain? Okay, so we can map these relationships very simply, as we'll see here in next couple steps, but let's just do some quick derivations or review of this. Okay, so let's start with the resistor. So we have this resistor in time domain. We got V equals IR. It's a simple relationship using Ohm's law in the frequency or phasor domain, except now our V is going to be a vector and our I is going to be a vector in this case. If we look at the relationship, in the figure, we have our real component, we have our imaginary component, both our I and our voltage are vectors, and then we have our angle phi here. Okay, so let's go ahead and define this mathematically. Okay, if we begin with this resistor, and we want to look at the current through this resistor, we can define the current as I equals Im cosine omega t plus phi. Okay, we can take Ohm's law, so we know V equals IR, which is going to give us R Im cosine omega t plus phi. So this is going to be our V in time domain. We can take the phasor form of this voltage, and we can say V is equal to R Im in the angle phi. Okay, and then we can take this phasor representation of the current, and then we can say I phasor, the vector is Im of this angle. So that's how we come up with V vector, our resistor, and then I as a vector. Okay, so that's how we came up with this relationship here. Okay, so that's a simple mapping between our time domain and then our frequency domain. We can do the same thing for the inductor, same concept, and let's just go ahead and do that. Okay, so let's scroll back up here. Let's just bring this up for inductor. So we defined our current for our resistor. We can do the same thing for the inductor. So for our inductor L, I is going to be, I'm just going to say, we're going to go through this process again. I is equal to Im cosine omega t plus phi. Okay, the voltage across this inductor is going to be V equals L di over dt, which is going to give us minus omega Lim sine omega t plus V. Okay, and then we know that minus sine A from previous definition is equal to cosine A plus 90. So we can change this, and we can say our vector V is equal to, so that's how we got that previous equation there. Then we can go ahead and define this, and we can write the voltage as V. Actually, before I do that, I don't want to skip this step. Let me take it one step at a time. Just keep it in time domain for now. V omega Lim cosine omega t plus phi plus 90 degrees. And then we can transform this into phasor. Okay. Our vector v is equal to omega L I m e to the j phi plus 90 degrees, which equals omega L I m e to the j phi e to the j 90 degrees, which is equal to omega L I m, the angle phi plus 90 degrees. But we know that Im of the angle is just the vector I, and we know that E j 90 degrees is just j, so then we can rewrite this relationship as our vector v j omega L in our vector I. Okay, so that's how we derive this relationship here. So if we look at this voltage, this is how we can convert it in the relationship. You'll see is going to be this graph here. Okay, so inductors in this case have a phase shift, so there's going to be a phase shift okay, between the voltage and the current. So we have, so actually the phase shift is here between voltage and current. Okay, in this case we can say the voltage leads the current by 90 degrees. Voltage leads current by 90 degrees. Or you could also say that the current lags the voltage, which is the standard convention. Okay, so you can say the current lags the voltage. Okay. And if we look at the diagram, the phasor diagram here, it's going to be by a positive phase angle. So this is represented on this phasor diagram by a positive phase angle between the voltage and the current. Okay. Okay, so that's the transformation for the resistor and the inductor. We can do the same thing for the capacitor. So let's go ahead and bring this guy up. Okay, so we have the capacitor as well, and then here we'll see that the capacitors have the opposite phase relationship as compared to the inductor. So here the inductor, we had V leads the current, as opposed to the inductor there, as opposed to in the capacitor, the current is going to lead the voltage. Okay, so let's go ahead and make a note of this here before we start. So the capacitors have the opposite relationship as compared to inductors. here the current leads the voltage. Okay, so up here we had the current lags the voltage for the inductor. For the capacitor, the current leads the voltage. Okay. And then we can further derive this here. So our relationship here, going from our time domain to our phasor domain, is this. Let's go ahead and derive this as well. Okay. So for the capacitor, we assume the voltage V is equal to Vm, and this is the voltage across the capacitor, cosine omega t plus phi. We say the current through the capacitor is equal to C dV dt. Okay. And then we can follow the same steps as we did previously, and then we get I, our vector I is equal to j omega CV, that's a vector, which can be rewritten as V, our vector, is equal to I, which is the vector, j omega C. Okay. And this is our transformation between the two, our relationship between the two here, between the time and the frequency domain. Okay, and then we can have a summary here. We have a summary table between the two, between the three different elements. Let's go ahead and make this bigger. So this is the summary of the voltage current relationships for the different elements RLC in time domain and frequency domain, time domain, frequency domain, and then we got time domain, frequency domain. Okay, for RLC there, and we can go back and forth between the two. So this again is the next step in coming up with AC circuit analysis and relating phasors and simplifying essentially the math, in our circuit analysis. Okay, so again, this is the phasor relationships of circuit elements from going from time domain to frequency domain. So when we do the analysis in the frequency domain, these are the equations we're dealing with. And then next we'll talk about impedance and admittance, and then we'll go over some examples.